RC time constants. So for RC time constants, let's say I happen to have a circuit. So this represents a switch, S1. This represents C1. This represents R1, and this represents my voltage source. And let's go ahead and make this not so challenging. Let's go ahead and make this a 10-volt source. And let's go ahead and give a value to the resistor. And let's say the resistor happens to be equal to 470 ohms. And let's say the capacitor happens to be a number 324. Okay, and so what we need to do is, first of all, C is equal to some kind of farads. And then we're going to calculate this here, TAU, and that's equal to time constant. And time constant is going to be calculated as the value of R times the value of C. And that's going to be equal to some number yet to be determined. So we have a little bit of work to do. So get your calculators ready. And as you get your calculators ready, we'll go ahead and make these calculator exercises here. First thing we need to do is to interpret the 324. What kind of value is it in terms of capacitance? So, Rebecca, 324. So how do I interpret this? This would be a what? First digit is a?
It's a 3.
3. Second digit is a?
2.
2. And then the, how many zeros?
4.
4 zeros, followed by what symbol?
Picofarad.
Pico, and then the units are in units of farads. Okay, so this interprets to be 320,000 picofarads, but we know that that's not proper engineering. So what would you write down in here as an answer that would be in proper engineering notation, Rebecca?
B.
I didn't quite hear it all. We still didn't quite hear it all. Yeah, give you a moment, pop that into your calculator, 320, 10 exponent negative 12, and your calculator spits out what?
320 nanofarads.
Perfecto. So 320 nanofarads. Okay, is everybody all right with that interpretation? Any questions on how that's interpreted? Okay, the next thing we need to determine is this thing called time constant. And time constant is given as this symbol, looks like a cursive T or maybe half of a pi. It's called tau, it's a Greek letter, and tau is calculated as the value of R times C. So the value of R in this case is 470. The value of the capacitor we have to key in as 320 nanofarads. So this multiplication exercise is going to be 470 times 320 exponent, and this is a negative, and nano was 9. So we're going to do this keystroke sequence. 470 times 320 exponent negative 9 equals. So what does that calculate to be? Let me go ahead and do this with you. Question will go to Pauline. Do you happen to have that yet?
I'm getting I'm getting 100.
Yeah, so go ahead and key in 470 times 320 exponent -9 for the nano, and then hit equals. And we'll
did you hear me? Sorry.
I didn't hear that fully, no.
Oh, sorry. I am getting 150.4 microseconds.
Okay, as my calculator does the same. So I have the 470 times the 320 exponent -9. I get 150.4 exponent -6. And so that was called out correctly as being 150.4 micro is the -6, and tau in units of time is not in farads, it's not in ohms, it's not in volts, it's not in amps. Time is measured in what units, my friends? Is measured in seconds. And seconds is shown with a lowercase s. It is not a capital S. Capital S is a unit of conductance called Siemens. So it's a lowercase s. So is everybody okay with one time constant being 150.4 microseconds? So the next question to be asked will be this: time for full charge equals question mark. And how do I determine the time for a full charge? Christian, Mr. Cortez, how do I determine the time for one charge?
Is it the 63% thing?
No, because if we refer for a moment, and let me help us out, refer for a moment back
3
to
divided by
this,
5.
back to almost, you're close. Take a look at this illustration here. This illustration is what we're going to be drawing in a moment. So the capacitor starts off with nothing at the very beginning in terms of voltage down here. 0 in time and 0 in volts starts here. The moment we close the switch, it'll start charging, and then it'll charge until it reaches full charge. But how many time constants are shown here on the bottom is what I want you all to focus your attention on. So we have 1, 2, 3, 4. How many tau? How many time constants to reach full charge?
5 time constant.
5. So the process is to do this. We know it's, so the time for full charge will be equal to tau times 5. So whatever we calculated for tau up here, the 150.5 microseconds, is going to be multiplied by 5. So 150.4 microseconds times 5 will give us this number here. I will just simply do times 5. And the answer to that one, Gabriel, what do you calculate? 150.4 micro, which is 10 exponent negative what? Gabriel, turn off your mic. Turn on your mic, I'm sorry.
-6.
-6. So 150.4, 10 -6 times 5. What do you calculate as your time for full charge?
150.4.
Micro will be multiplied times 5.
Oh, okay. 150.4.
Micro. Don't forget the micro. 10 exponent -6.
752 microseconds.
Okay. And my calculator verifies your calculation is correct. So 752 microseconds. That's the time it takes for this capacitor to reach full charge based on the circuit that I have here of 470 ohms and a number 324 cap. So let's show you what happens here graphically. And I'll try to do this to the best of my ability this way. I'll go ahead and draw an axis going like so, and I'll go ahead and draw an axis going like so. 2, 3, 4, 5. Okay, so something like that is good. And I'll use these graduations here. So this is 0. This is 1, 2, 3, 4, 5. So this axis represents time in units of tau. This axis here represents two things. It will represent a V for volts, and it will also represent I in amps. It'll represent voltage and current, okay? And so let's see what happens with this. If I have a maximum, and let's see, let's do. Okay, so if I graduate this one this way, okay, so this will represent 2.5 V, 5 V, 7.5 V, 10 V. If I just graduate it this way, my maximum line would be somewhere around here. Somewhere around there would be my maximum, okay? So this would be max. And, oh dear, smudge, oh well, can't happen, can't help that. Let's go ahead and do this. 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 And go ahead and do this. All right, so there's my intervals: 0 tau, 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. And let's go ahead and plot what happens with respect to voltage based on the textbook illustration. My maximum voltage is 10 volts, yes? And in the first time constant, what happens here is this. Let's go ahead and pop this in here this way. In each time constant, the cap will charge / discharge. Would somebody turn off their microphone, please? Because there's some background noise. Thank you. So in each time constant, the cap will discharge 63.2% of the remaining value. That is a very important characteristic of logarithms and how this all behaves. And we won't get into a discussion of how the logarithm is derived and how the exponential curve comes about. Just accept that this is a simpler way of determining what these numbers are going to be. 63.2%. What is 63.2% as a decimal? Isn't 63.2% as a decimal going to be 0.632? Is that right, everybody? Okay, so here we go. We're going to determine initially our voltage is going to be here. It's in green. There's my green dot. And what happens in the first interval between 0 and 1 tau? Within 1 tau, the amount of voltage that the cap will charge will be 63.2% of what? Of the remaining value. Well, what's remaining, if we're starting at 0, what's remaining is the full 10, yes? So what you're going to do is you're going to multiply 0.632 times 10. So in first tau, 0.632 times 10 volts will give you what? 6.32 volts. And graphically, where does 6.32 volts sit? It's approximately right here. It's above the 5, so I'm just going to approximate a green dot right there. Is everybody okay with how we landed that first dot and how that number came about? Any questions how this number came about? This is presently 6.32 volts. Any questions on that?
Is that a 0.672 times 10 volts or 632?
This is 0.632 times 10 volts, which is same decimal that I wrote there in red, which is the same as 63.2%. Is that a little better there for you, my friend? Now, I'll try not to write so small.
Yeah.
Okay, all right. But yeah, please don't hesitate to ask any questions. But are we okay with how that number came about? Okay, so here's the thing. Here's what's fascinating about all of this. If this is where we're at, how much is left? How much is remaining? How much is remaining is not the full 10. How much is remaining is going to be 10 minus 6.2. What's 10 minus 6.32?
3.68.
3.68, right? So what's left right here is 3.68 volts. That's what's remaining. So remaining, I'll do some darker ink. Remaining equals 3.68 volts. That's what's remaining. So what's going to happen in the next time constant? In the next time constant, so I'll write down, in second time constant, what we'll do is 0.632 is going to multiply the remaining value of 3.68, right? So 3.68. This is how much more the capacitor will charge. And mathematically, let's all go ahead and do that on our calculators. So we will take 0.632, and we're going to multiply that by 3.68. And your calculation works out to be what? Mr. Rolando, help us out here. What do you get?
Uh, 68.
I didn't hear an answer. Are you still calculating, sir?
Okay, I got 2.33.
Okay, so it works out to be 2.33 volts. Is that everybody gets? Okay, well, you can turn off your mic now. Or turn, yeah. And then, so does everybody verify 2.33 volts is what this calculates to be, yes? So 2.33 volts. Has to be something less than 3.68. So the 63.2% of this is this. Now, this tells you how much more the capacitor charged. So what we're going to do is we're going to add to this number, and we will get the new value of what the capacitor is now. So we are going to add this to 6.32, and the new value works out to be 8.65 volts. So our new point here will be here above the 7.5, and we will put this here, and this will be 8.65 volts. Are we okay with how that's calculated? And guess what? If we repeat this exercise for the third tau and the fourth tau, we'll do one more tau, okay. In third tau, what will happen? What will happen between the second and third tau is the cap will charge 63.2% of what? The remaining value. What is my remaining value if I'm currently up to 8.65? This will work out to be 0.632, and we're going to multiply it by what's remaining. Can someone tell me what this number will be? I will call on Andrew. Can you tell me what is the remaining? If I have 8.65 where the cap charges up now, and my maximum is 10, how do I find what's remaining, the difference between these two numbers?
What's remaining? 1.35.
Exactly. It is 1.35 volts is what's remaining. Excellent. So when we go to do this calculation, we will go ahead, pop our calculator back in, and
I got 853.2 milliamps.
0.632, and we're going to multiply by 1.35. You almost called it out correctly. It's not milliamps. It's voltage.
Oh.
So you
Millivolts.
called out. Go ahead. You called out.
I just 8 point, what was it? My calculator just cleared on me. What, 8.5? It was 8.5. 8.5.
Okay, everybody should have 853.2 millivolts.
Millivolts. Okay.
That's how much more this will charge. Well, what are we going to do with this amount? We're going to shoot this up here and add to the previous plateau, because we have reached different plateaus along the way. The first plateau was 6.32 volts. The next plateau was 8.65. We have to add this incremental amount to the previous one. So we'll go ahead and do that. There's my 853.2 milli, and I'm going to add that to 8.65. Boom. What do I have? That will generate a new plateau of 9.50 volts. Is everybody okay with that value? 9.50 volts. Any questions how we determine that next plateau value, which will plot right about here, and that's 9.50 volts. Okay, 9.5 volts. So what happens, okay, without doing the mathematical derivation for the third tau and the fourth tau, we can do that. Basically, if you look at this, the dots, are we getting closer and closer? Ultimately at 5, we are so close to 5, we pretty much put our last dot right there. And if we go to connect the dots, we end up with an exponential curve that looks something like this. Here, 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 and here. This is how voltage charges over 5 time constants for this particular resistor and this particular capacitor. And how much time is that? Well, let's go ahead and analyze this again. We determine each time constant by multiplying the R times the C as 150 micro. So that means from here to here, I have 150.4 microseconds. From here to here, I have another 150.4 microseconds. Well, in total, how much do I have for the 5 time constants will be 150 0.4 microseconds times 5, and that will give me 752 microseconds for the total time for this to reach full charge. Is everybody okay with that curve, how it's drawn? Is everybody feeling comfortable about how these numbers are determined? And they're determined by the rate of charge of the capacitor based on this R value, the C value, and it can only go increments of 63.2%, but the keywords are what? 63.2% of the remaining value. Okay. That is the charging curve for voltage. What does this look like for current? Current is at maximum at the very beginning. I'm going to put a red dot for current. I'm going to write over here. Current is at maximum at the beginning. So the moment we close the switch, right here at 0, my voltage is nothing, but my current starts flowing immediately to start charging the cap. As the cap is charging up, the rate of current flow will decrease. So at what rate does the current decrease? Listen carefully. The current will decrease 63.2% of the remaining value. Check this out. If it started here at maximum and the goal is for current to go down to 0, 63.2% of this range from maximum down to 0 puts us at a red dot right about there. So the current will drop from here down to here within 1 tau. How much will the current flow drop in the next time constant between this point and 0? Well, what is 63.2% of this line? Something more than half. So I will put a red dot right about there. What will happen with current as it decreases further between 2 tau and 3 tau? Well, what's the remaining value? The remaining value is from here to here, this little short line. And 63.2%, little more than halfway down, puts us right about there.
So could you take these, you know how we times it by 10 at first, and then we got 3.68? So we would put that on the first one and then keep on coming down?
Yeah, we won't do the math to derive this, but I just wanted to show you that the current is an opposite curve to the voltage. Okay, that's the point I'm trying to show you. We won't do another set of math for this probably ever again. And then the next red dot is here, and then the next red dot is here. And so current will come down from a maximum to here, drop to here, go down to here, continue to here, and finally down to no current. So when this has reached maximum voltage on the green curve, when this reaches the full 10 volts on here, there's no more current flowing. So the curve goes down to 0. And that's exemplified by our previous here. And let me go back one. Not capacitor values, but I want to go to here and go to here and okay. So the summary of this that I want to get to is this. The summary I want to get to is the moment we close the switch, 2 things are happening. The voltage starts charging from 0 and after 5 time constants reaches the maximum. At the same time, the current starts as maximum and starts decreasing down to 0. And so as you observe what's happening in this illustration, what quantity is at maximum first? What quantity is at maximum at the end? At the very beginning, what quantity is at maximum first? Now, maximum is this line right here. So which of the, is the green line at maximum at the very beginning, or is the red line at maximum at the very beginning? Rebecca, what do you think?
The red line.
Rebecca?
The red line.
The red line is at maximum at the very beginning. Does everybody observe that? If this is my maximum line here at 10, at 0 tau, at the very beginning, current is at maximum first. And then after 5 tau, the current goes to 0, then what quantity reaches maximum at the end is voltage. So here we can make a very strong and profound concluding remark. The concluding remark that I want you to take away from all of this, what we want to conclude with is here. Current, so this is VIP. VIP stands for very important point. And I'll do this in red. Very important point is current leads voltage. Current leads voltage. Or you could also say voltage lags current. That's a very, very important point. Include this with, and I'll tell you why that's significant in a little bit, but you want to write that down. So this is what type of circuit? This is an RC circuit, because there's an R and there's a C. And we're talking about time constants. Time constants are the amount of time for a cap to rise or discharge 63.2% of a remaining value. And so if we work out all the numbers for this exercise, we end up with these two lines, a red line and a green line. And as you observe, from the beginning to the end, the quantity that is first is current, and at the end, the quantity that reaches maximum is voltage. And that allows us to make this concluding remark. Current leads voltage, or you could also say voltage lags current. What does lag mean? Lag means to follow behind. Okay? Is everybody all right with that so far?